the problem number 8. Okay, on I section. Completely the problem is solved. So we will move on to the next problem. Okay, problem number 9. You just go through it before going to solve it. A midspan section of a simply supported girder of span 8 meter is a symmetrical I section. Okay, it is a symmetrical I section. 250 by 500 mm overall. Let me write the diagram for the same. If you write the diagram, it will be helpful for us to solve the problem accordingly. Okay. Solution. He says that it is a symmetrical I section with 250 mm by 500 mm overall. Means width of the flange is 250 mm. Overall depth of the I section is 500 mm. Okay. Let me write the symmetrical I section.
Sir, 2 minutes will write down questions, sir.
Okay. Finished? Finished writing the question?
Yes, sir.
Okay. So here you just go through it. It's a symmetrical I section having 250 mm by 500 mm overall. Same thing I written in the figure. 250 mm is the width and overall depth is 500 mm. Further, he says that the flanges are 100 mm thick. Okay, flanges are 100 mm thick. Same I have mentioned in the figure. And the web is how much? 80 mm thick. Web is 80 mm. Here web is 80 mm. Okay. Flange thickness is 100. The girder carries an UDL live load of 10 kilonewton per meter. Okay. And he says that the load acting on the beam is a UDL live load. And the intensity of load is how much? It is 10 kilonewton per meter. Intensity of the load is 10 kilonewton per meter. And the span of the beam is given at the beginning. It is 8 meter. Span of the beam is 8 meter. Okay. The question is to determine the initial pre-stressing force and its eccentricity so that no tension is allowed in concrete both at transfer and service load. Okay, and the loss of pre-stress is given. It is given as 18%, and the density of the concrete is given as 25 kilonewton per meter cube. Okay, so this is all the given data. Okay, and he has given two specific conditions. Okay, the first condition is no tension is allowed in transfer condition. That is the first condition. The second condition is no tension is allowed in service condition. Okay, let me utilize these conditions given in the problem and we will solve the unknown parameters, that is pre-stressing force and its eccentricity. Okay, we have to find the magnitude of the pre-stressing force and its eccentricity from the neutral axis such that no tension is allowed at both transfer and service load. Means the stresses at the bottom fiber is 0. Okay, during service load, and stresses at the top fiber is 0 at the transfer condition. Okay, so given data is, he has given two condition. Case 1, it is no tension allowed during transfer. This is what the condition, first condition. Okay, and one more condition, no tension is allowed during service load. So that condition will utilize later. Will utilize later. Okay. Now let us understand what is the meaning of no tension allowed during the transfer. Okay. So you all know already the process of uh, pre-stressing in a beam. Okay. So what is the process of pre-stressing? The tendons will be stretched to a required stress. Then the concrete is poured and it is allowed to harden. Then after that we'll cut the tendons at the edge. Okay, so that the pre-stress will be transferred to the beam. That condition, whatever we call it as transfer. Okay, that condition, whatever we call it as transfer. And one more thing, let me go to the starting, that is introductory part of the model. Here what we'll be doing is same thing I explained before. The tendons will be stretched and the concrete will be placed. After that, the tendons will be cut at the ends so that pre-stress will be transferred to the beam. Okay. See here, you can see transferring the pre-stresses. Okay. Transferring the pre-stresses here you can see. Correct. So at this condition, he says that the tension is 0. So where the tension is taking place now? So at the transfer condition, the tension is taking place at the top fiber. You can see, okay, tension is taking place at the top fiber. Therefore, at top fiber, you know the formula for finding the resultant stress. What is the formula for finding the resultant stress? At top fiber, you already know the formula, that is P by A minus P by Z plus mg by Z plus mq by Z. Okay, this is the formula. But as this is transfer condition, still the live load is not applied. Okay, still the beam is not subjected to the live load. Okay, still it is in the manufacture state. Okay, still it is not put into working condition. Okay, therefore this live load will not come into picture here. At which condition? At transfer condition. Okay, I hope you are understanding. Okay, so this live load will not come into picture during the transfer condition. Okay, still the beam is not applied with the live load, just the pre-stresses are transferred. Okay, dead load will be there, mg will be there, dead load moment will be there, but live load moment will not be there. Therefore, we can take the condition as P by A minus P by Z plus mg by Z is equal to 0. Okay, I hope you understood. P by A for transfer condition, the let me write the figure during the transfer condition. This is the bending pattern of the beam. Correct? Huh? So here the pre-stresses, when pre-stresses are transferred, so this is what the bending pattern of the beam means. At top fiber, the tension will occur. Okay, at top fiber tension will occur, and he says that during transfer condition tension at the top fiber is, okay, the tension is 0, means at top fiber sum of stresses is equal to 0. Therefore the condition is P by A minus P by Z plus mg by Z, but there will not be effect of moment. Okay, this will not be there. Okay, during transfer condition, remember. Okay, still at the transfer condition, it is still the beam is not subjected to working condition. When it is put into working condition, then only the live load will act on the beam. Okay, therefore we will utilize this condition P by A minus P by Z plus mg by Z. Okay, so here A is cross section of the beam that you can easily calculate. A is equal to cross section of beam. A is equal to, you can calculate it, correct? So all the dimensions are known. Let me calculate the effective the depth of the web. If you calculate the depth of the web, how much you will get? Overall is 500, correct? 500 on either side, 100 mm thick flanges are there. 500 minus 100 minus 100. Okay, 300. 300 will be the depth of the web here, web portion. 300 is the depth of the web portion. Okay, so if you can calculate the overall area will be 250 by 100 into 2 number of flanges plus 80 by 300. Okay, therefore here 250 by 100, 250 by 100 plus area of flange, flange into 2. There are 2 number of flanges into 2 number of flanges plus area of web 80 by 100, 300. 80 by 300. Okay. So what will be the total area of the cross section? Area is equal to, so you please cross check the answer, 74,000 mm square. All of you please calculate and cross check the answer. If you get any other answer, any different answer, let me know, we'll correct it. Okay. So 74,000 mm square. So for calculation of the self weight, we need the area in terms of meter square. Convert this area into meter square. It will be 74,000 into 10 power minus 3 whole square. Okay, 10 power 3 minus 3 whole square. So the final area, if we calculate, it will be 0.074 meter square. Okay, 0.074 meter square. So area in terms of meter square is required for calculation of the self weight, correct? Now we got the area. Pre-stressing force, that only we are intended to calculate. We have to calculate that is only the unknown parameter here. Okay, leave as it is. And eccentricity is also need to be calculated. It is also unknown parameter. Leave. Then what next? Z is there. Okay, section modulus is there, that you can calculate section modulus. So we know that section modulus Z is equal to, what is the formula? That is equal to I by Y. Okay, that is equal to I by Y. So where I is the moment of inertia. So first you calculate the moment of inertia of the I section. So what is the moment of inertia of the I section? How you will calculate? So it is a symmetric I section. So easiest way of calculation of moment of inertia of a symmetric I section is, so before we have calculated once for similar kind of problem. Let me hash this portion. Okay. So what is the width of this rectangle? Let me know. See, overall width is 250. Okay. Overall width is 250. 250 minus web thickness 80 if you do, you will get how much? One 170 will get 170 divided by 2 if you do, you will get 85 mm as width of this rectangle of the hatched portion. 85 on either side. So you can easily calculate the moment of inertia. How you can calculate? Moment of inertia of the I section will be equal to moment of inertia of the full area. Okay, minus 2 into moment of inertia of this hatched rectangles. Okay, let me calculate here. We know that the moment of inertia of rectangle is BDQ by 12. First, you calculate moment of inertia of the whole area. So 250 into 500 cube divided by 12. I is equal to BDQ by 12. Okay, therefore I is equal to moment of inertia of the full area. Okay, let me write it. Moment of inertia of full area of full area minus moment of inertia of shaded area. Don't simply listen to the class. Please write. Please solve along with me so that you can understand in a better way. Okay. So moment of inertia of full area is overall width is 250, overall depth is 500. Therefore, it is 200 into 500 cube divided by 12. Okay. 200 into 500 cube divided by 12 minus moment of inertia of shaded area. Okay, there are two shaded rectangles on either side. First, you calculate moment of inertia of any one rectangle. 85 is the width of rectangle, 300 is the depth of the rectangle. Therefore, it is 85 into 300 cube divided by 12. 85 into 300 cube divided by 12 into 2. Why into 2? There are two such kind of rectangles having hatched portion. Okay. By this,
Sir,
you'll get moment of
250
inertia of
into
the.
300 cubes.
Yes, yes.
250 into 300 cube, no, sir.
250 into 300.
For full area, you have written 200 in this.
Moment of inertia of full area means, see here, moment of inertia of the full area, this area. Let me write. Let me show you. So moment of inertia of this whole rectangle. Okay. Moment of inertia of whole rectangle means you need to take overall width 250, overall depth 500. So that is what it is 250 into 500 cube divided by
Yes,
12.
sir. You have written 200.
Oh, sorry. 250. Let me correct it. 250. And the moment of inertia of the shaded area. 85 into 300 cube divided by 12 into two numbers. So by this, what is the answer that you get? You check the answer. Please cross check the answer. 2.22 into 10 power 9 mm4. Please cross check the answer. Okay. Now you got moment of inertia. Then y is distance of the centroidal axis. So this I section, whatever it is given, it is symmetric. Okay, it is a symmetric I section. For symmetric I section, the y distance of centroid, okay, from top fiber or the bottom fiber is equal to directly overall depth divided by 2. Okay, y is equal to 500 divided by 2. So you will get 250 mm. 250 mm. Okay, therefore section modulus Z is equal to I is 2.22 into 10 power 9 divided by 250. Okay, the answer is 8.88 into 10 power 6 mm cube. Please cross check the answer. Okay, by this you got section modulus. Then what else is required? Mg is required. What is Mg? Moment due to dead load of the beam. Okay, moment due to dead load of the beam. To calculate moment due to dead load of the beam, you need what is the intensity of the dead load. Okay, first you calculate dead load moment. Dead load moment. First you calculate the self weight or dead load of the beam. Self weight of beam is equal to, how we will calculate? Self-height of the beam. Cross-sectional area multiplied by density. Density will give the self-height of the beam. Okay. Cross-sectional area is how much? Just now we have calculated just before. See here, density is given in terms of kilonewton per meter cube. Okay. And area should be substituted in terms of meter square only. Okay. 0.074 meter square. 0.074 meter square into density of the concrete. It is given as 25 kilonewton per meter cube. Sometimes they will give, sometimes they will not give. If it is not given, you need to assume it as 24 kilonewton per meter cube. Even if you assume 25, no problem. Into 25. Okay. If you calculate the answer, it will be around 1.78 kilonewton per meter. Okay. Self-height of the beam. Cross check the answer. Now you got intensity of the self-height of the beam, that is 1.78 kilonewton per meter acting over a span of 8 meter. Okay, you can calculate the dead load moment easily. Therefore, dead load moment mg, okay, mg is equal to wgl square by 8. Okay, this is dead load intensity wg is 1.78 into 8 square by 8. By this you will get dead load moment. Answer is 14.24. Please cross check. 14.24 kilonewton meter. Okay, in terms of Newton millimeter, 14.24 into 10 power 6. 10 power 6 Newton millimeter. Okay, now you got all the required parameters except the unknown parameters, pre-stressing force and the eccentricity P and E. Except the P and E, you know the remaining things. You just substitute. P by A, correct? First term is P by A. P is the unknown factor. Keep as it is. P by area. A is how much? Area is 74,000 mm square. So here you need to substitute the area in terms of mm square. 74,000. Okay. Then P by A. After that minus PE by Z. Minus PE by Z. Z is calculated. It is 8.88 into 10 power 6. 8.88 into 10 power 6 minus PE by Z plus mg by Z. mg is 14.2 into 10 power 6 divided by Z is 8.88 into 10 power 6. 8.88 into 10 power 6 is equal to 0. Is equal to 0. Okay. Now you will get an equation. Okay. 1 by 74,000 is equal to how much? 1 by 74,000, if you calculate, you will get 1.35 into 10 power minus 5 into P minus 1 by 8.8 into 10 power 6. If you calculate, you will get 1.13. Please cross check the answers into 10 power minus 7 PE. Keep as it is plus. So value of this third term, if you calculate, it is 1.60. 1.60 is equal to 0. Is equal to 0. Okay. Call this as equation number 1. Call this as equation number 1. Now Utilizing the first condition, that is no tension allowed during transfer, we have formulated an equation in terms of P and E. Similarly, there is one more condition given in the problem, that is no tension is allowed. Okay, no tension is allowed during service load as well, during service condition of the beam as well. Okay, for that we'll write the formula and we will formulate one more equation. Solving the both, we will get the required parameters, that is prestressing force and the eccentricity. Okay, during the service condition, what happens? During service condition, what happens? There will be lie load acting on the beam during service condition. Okay, there will be lie load acting on the beam. Due to this lie load, the bending pattern of the beam is vice versa, like this. Okay, vice versa. Okay, therefore tension occurs at the bottom fiber during service condition. Okay, tension occurs at the bottom fiber during the service condition. Okay, when the lie load is applied on the beam, this is what the bending pattern. So tension occurs at the bottom fiber. Okay, tension occurs at the bottom fiber. At bottom fiber, you know the formula to calculate the tension. Your formula to calculate the resultant stresses. What is the formula? P by A plus P by ZB minus mg by Z minus mq by Z is the formula to calculate stresses at the resultant stresses at the bottom fiber. I will take the same formula. Second condition, let me write the second condition. Case 2. In between, if you get any doubts, you can. Yes, yes. Any doubt? Second condition is no tension is allowed during service condition. During service condition. No tension is allowed during service condition. Okay. Therefore, the during service condition, the tension occurs at the bottom fiber. So the resultant stresses at the bottom fiber is calculated as P by A. Therefore, P by A plus PE by Z minus mg by Z minus mq by Z is equal to 0. In this case, the lie load, moment due to lie load come into picture because lie load is applied during the service condition. When the beam is put into service, then obviously there will be lie load acting on it. Okay, therefore, mq will come into picture here in this case. Okay, and one more very important thing here, he has given loss of pre-stresses. Okay, loss of pre-stresses, how much it is given? 18%. Okay, that loss of pre-stress should be considered during the service condition. Loss of pre-stress should be considered during the service condition, not in the transfer condition. Okay, transfer condition, it is just the beginning state of the pre-stressed concrete beam or beginning state of the pre-stressing. Okay, in that case, there won't be any losses. When the beam is put into service, then only we can observe losses of pre-stresses. Okay, about the losses of pre-stresses, I will be discussing in detail in the next model. Okay, model 2 is of study on loss of pre-stresses only. Okay, so remember this much. The loss of pre-stress should be considered during the service condition, not in the transfer condition. Okay, this much you remember for now. Therefore, considering the loss of pre-stress, okay, the loss of pre-stress is given as 18%, 18%, okay, and it should be considered only in working condition, not in transfer condition. Okay, therefore the effective pre-stressing force will be the effective pre-stressing force force will be equal to P. Okay. Initial stress is P. In that there is 18% loss of stress. 18% means 18 by 100. Nothing but 0.18. So in the overall pre-stressing force, initial pre-stress, there is loss of 0.18 P. Okay. So you will get effective pre-stressing force as 0.82 P. Okay. If we call this as equation number 2, so equation 2 becomes, we can rewrite the equation 2 now with by considering the loss of pre-stresses. Therefore, equation 2 becomes P by A. P is nothing but 0.82 P, 0.82 P by A minus PE by Z, sorry, 0.82 PE by Z, 0.82 0.82 PE by Z, then minus here plus no minus mg by Z, then minus mq by Z is equal to 0. Okay, I hope you understood this concept. Now, what is next step? Just substituting all the values and getting one more equation. Okay, here one more term is added, that is mq by Z, where mq is moment due to live load that you calculate initially and substitute all the values. Live load moment mq is equal to wq L square by 8. Okay, wq is given, means live load acting on the beam is given. How much it is given? 10 kilonewton per meter is the live load that is acting on the beam. This is wq. Okay, so 10 into 8 square by 8. 10 into 8 square by 8. So 8 get cancelled. You will get 80 kilonewton meter, or 80 into 10 power 6 Newton millimeter. Okay. The remaining parameters are known. Section modulus already we have calculated. Area of cross section is also we have calculated earlier. Just substitute all the values now. Therefore, if you call this as equation number 3, therefore the equation 3 becomes, therefore equation 3 becomes 0.82 P by A. 0.82 P is the unknown parameter. Area is how much? It is 74,000 plus 0.82 PE by Z is 8.88 into 10 power 6. 8.88 into 10 power 6 minus mg by Z. What was the mg value? It is 14.2 into 10 power 6. 14.2 into 10 power 6 divided by 8.88 into 10 power 6 minus mq is 80 into 10 power 6 divided by 8.88 into 10 power 6 is equal to 0. By this you will get one more linear equation, correct? 0.82 divided by 74,000. How much? 0.82 divided by 74,000. So it is 1.11 into 10 power minus 5 P. Please cross check. Plus 0.82 divided by 8.88 into 10 power 6. How much? If you calculate, it is 9.23 into 10 power minus 8 PE. Okay, minus value of this whole term. Okay, value of this whole term, if we calculate, it is 10.61 is equal to 0. Okay, now call this as equation number 4. Okay, now you got two linear equations, that is equation 1 and equation 4. If you assume the term P as X and term PE as Y. Okay, unknown parameters X and Y. If you assume term P as X and term PE as Y, if you solve both equations, you will get the value of X and Y. X and Y means X is nothing but P, Y is nothing but PE. You can solve these two equations in your calculator itself. You already known with how to calculate these kind of linear equations. If you just calculate and uh, get the answer for P and PE means you will get the answer as P is equal to solving equations solving equations 1 and 4. Someone calculate the answer please. 1 and 4 and cross check the answer. Equation 1 is just see equation 1 is 1.35 into 10 power minus 5 P minus 1.13 into 10 power minus 7 PE plus 1.60 is equal to 0. This is the equation 1. Please note down and solve both equation 1 and the 4. Okay. The answer is P is equal to, if you solve, P is equal to, you will get it as minus 420.44 into 10 power 3 Newton. You will get the answer as minus 420.44 into 10 power 3 Newton. And this minus indicates the nature of the force. The nature of the force is minus nothing but compressive force. It is a compressive force. You can rewrite the answer as 420.44 into 10 power 3 Newton. Nature of force is compression. Okay. So this is the prestressing force. Similarly, if we calculate the value of PE, okay, by taking PE as Y, unknown parameter, you will get the answer for PE as minus 64.388 into 10 power 6. Okay, into 10 power 6 Newton millimeter. Newton millimeter. Okay, so what this minus indicates? What this minus indicates? It is sagging bending moment. Sorry, hogging bending moment. Okay, it is a hogging bending moment. Okay, therefore we can take simply as 64.388 into 10 power 6 Newton millimeter hogging. Okay. Now prestressing force P is known. Okay, therefore P is equal to 64.388 into 10 power 6. If you substitute the value of P here, that is 420.44 into 10 power 3 into eccentricity E as it is equal to 64.388 into 10 power 6. You will get the value of eccentricity. Okay. You will get the value of eccentricity. What is the answer? Anyone? If you calculate it, tell me the answer. You please cross check it. The answer is 153.14 millimeters. So we got both prestressing force and its eccentricity, which means that if we apply a prestressing force of 420.44 kilonewton with an eccentricity of 153.14 millimeter, there won't be any tension at the both transfer condition as well as service condition of the beam. This is what the meaning. Okay. So to this solution gets over. If you have any doubts, you can ask before moving to the next problem, students. Any doubts? Okay. We move on to the next problem. Problem number 10. Okay. Problem number 10. All of you go through it and understand what is given in the problem, what is to be determined. All those things you first understand and you can proceed with solution. Okay. A concrete beam of symmetrical I section has an effective span of 8 meter. Okay, here also it is symmetrical I section only. Effective span is 8 meter. Width of the beam is 400 mm and depth 500 mm. Web thickness is 80 mm. Okay, the beam is prestressed by a parabolic cable with an eccentricity of 150 mm at center and 0 at the supports. Let me write the diagram so that you can understand. Solution. Solution. He says that it's a symmetric I section. Let me write the diagram of a symmetric I section.
Sir, question.
Yes, please write. Finished? Finished the writing of the question?
Yes, sir.
Okay. I have written the diagram. He says that a concrete beam of symmetrical I section, I have written the symmetrical I section, has an effective span of 8 meter. Span is 8 meter. The beam is prestressed by a parabolic cable with an eccentricity of 150 mm at the center and 0 at the supports. And he says that web thickness is 80 mm. Web thickness is 80 mm. Flange thickness, it is not given actually, correct? Flange thickness is not given. So in this, in such cases, whatever the web thickness given, we'll assume the same thickness for the flange only. In case of unavailability of the data, we can assume 80 mm as flange thickness as well. Okay. And he says that the beam is prestressed by parabolic cable. Okay, let me write. This is the whatever the figure I have written. It is cross section of the beam. If I write longitudinal section of the beam, if I write longitudinal section of the beam, he says that the length of the beam is 8 meter. Span of the beam is 8 meter. 8 meter. Span of the beam is 8 meter. You just go through. The beam is pre-stressed by a parabolic cable with an eccentricity of 150 mm at the center and 0 at the support. Okay, eccentricity at the center of the span. Okay, eccentricity at the center of the span is around 150 and 0 at the support. Eccentricity of the cable is 0 at the support and 150 mm at the center of the span. Okay, so therefore it is a parabolic cable. Parabolic cable having 0 eccentricity. There is no distance between centroidal axis and the cable. Okay, 0 eccentricity at the support, and there is an eccentricity of how much? Eccentricity of 150 mm at the center. Okay, at the center the beam eccentricity is 50 mm. Okay, this is what given in the problem. I hope you are understanding. So this is the prestressing force which acts through the cable. Okay, the effective prestressing force is 180 kilonewton. P is equal to 180 kilonewton. Okay, the live load on the beam is 8 kilonewton per meter. Let me write the diagram for the live load. Live load acting along the length of the beam is how much? 8 kilonewton per meter. Okay. Draw the stress distribution diagram at a 3 meter span from the left. Okay. What is the question here? We want stress distribution at 3 meter from the left end. What is the question? At 3 meter from the left hand. Let me call this section as XX. Okay, we want stress distribution diagram at 3 meter span from left hand. Okay, at this point we want the stress distribution, means we have to make all the calculations with respect to this section XX only, with respect to 3 meter from the support only. Okay, this is what the question. Okay, I hope you understood. Now we will proceed with solving the problem. So to calculate the resultances, what are the things needed? We need prestressing force, we need cross-sectional area, we need dead load moment, we need section modulus, we need live load moment, we need the eccentricity. Correct? Okay, initially we will calculate all the parameters, then we can easily calculate the resultant stresses. Okay, what are the things we need? We need prestressing force, we need cross-sectional area. Correct? Then what else we need? We need eccentricity. Correct? Then we need moment due to dead load mg, we need moment due to live load mq. All these things are required to calculate resultant stresses at any section, whether it may be 3 meter from the left support or 6 meter, whatever. Okay, first we need to calculate all these parameters. Okay, now let us calculate one by one. Prestressing force P, it is given. How much it is given? 180 kilonewton. Okay, whatever it is given, we will take. If it is not given, we will calculate. Prestressing force. P is equal to how much it is given? 180 kilonewton. Nothing but 180 into 10 power 3 Newton. Okay. Then area of cross section. You can calculate area is equal to first you calculate the area of flange 400 into 80 will give area of flange into two number of flanges into 2 plus the depth of the web how much you will get 500 minus 80 on either side 500 minus 80 minus 80 how much you will get 340 I think 340 500 minus 160 okay 340 mm is the depth of the web okay therefore it is 80 is width into 340 is depth of the web. By this we get cross sectional area. So it is area is equal to if we calculate 91,200 mm square is the answer. 91,200 mm square is the answer. In terms of meter square, it is 91,200 into 10 power minus 3 whole square. Okay. So if you calculate, it will be 91,200 into 10 power minus 6 meter square. Okay, this area in terms of meter square is needed to calculate the self height of the beam, correct? Force P is for now we have calculated the cross sectional area. If you calculate the cross sectional area, you can calculate the stresses due to prestressing force, correct? Stresses due to prestressing force. What are the stresses due to prestressing force? There are two kinds of stresses. One is direct stress and one more is bending stress. Correct? One is direct stress and the one more is bending stress. P by A, P by ZT or P by Z. Okay. We can calculate P by A now. Therefore, P by A. Okay. And it is plus on both top and the bottom. Correct? P by A is equal to P by A is equal to P is 180 into 10 power 3 divided by 91,200 into 10 power minus 6. Okay. What is the answer? Sorry, it is 91,200. No? The load we have substituted in terms of Newton. Area we substitute in terms of mm square so that you will get the stress in terms of Newton per mm square. Okay. So it is 91,200. Calculate the answer. It is 1.97 Newton per mm square. Okay. So this is stress due to prestressing force, direct stress due to prestressing force. There is one more stress, bending stress, P by Z. There eccentricity E is involved. Correct? Eccentricity is P by Z. Okay. So to calculate Z, we need I and we need Y. Okay. Moment of inertia we have calculated. We can calculate as we calculated for the previous problem. I is equal to, we can divide this. You can take these two rectangles. Please calculate width of the rectangle. Width of the shaded rectangle, please calculate. How much it will be? Overall width is 400 minus 80. Web thickness 320 divided by 2. If you do, you will get width of each rectangle. 320 divided by 2 is 160. 160 and 160. So you can calculate the moment of inertia. So moment of inertia of this I section will be moment of inertia of the full area minus moment of inertia of the shaded area. Moment of inertia of full area is BDQ by 12, 400 into 500 Q by 12. 400 into 500 cube divided by 12 minus 160 into 340 cube divided by 12. 160 into 340 cube divided by 12. And there are two numbers of rectangles. Okay. By this we'll get moment of inertia. Please calculate the answer. It is 3.12 into 10 power 9 mm4. Please cross check the answer. If you are getting any other answer, let me know. We'll correct it. Okay. Now Y is here I section is a symmetric H section. Y is directly overall depth divided by 2. Overall depth is 500 and Y is equal to D by 2 500 by 2 250 mm. If it is unsymmetric, you need to calculate it. Okay, centroid you need to locate and you have to find ZT and ZB. Okay, therefore section modulus Z is equal to, therefore section modulus Z is equal to I by Y 3.12 into 10 power 9 divided by Y is 250. Please calculate. It will be 12.48 into 10 power 6 mm cube. 12.48 into 10 power 6 mm cube. Okay. Now we have calculated Z section modulus. What else we need? We need eccentricity E. Correct? We need eccentricity E. Write the side line as to find eccentricity E. To find eccentricity E. See what eccentricity you are going to take here, students. Very important step here. It is what eccentricity you are going to take. See, he says that the cable is having parabolic profile having 150 mm eccentricity at the center and 0 at the support. Okay. Now the question is which eccentricity you are going to take. Okay. You need to take eccentricity where the stresses are to be calculated. Here our interest is to calculate stresses at 3 meter from the left support. Therefore, you need to substitute corresponding eccentricity at that point only. Don't substitute 150 mm. It goes wrong. Okay, if you substitute 150 mm, then you are going to calculate stresses corresponding to center of the span. But we are interested to find stresses corresponding to the point at a distance of 3 meter from the left support. So we have to find this eccentricity. Now the question is how to find this eccentricity. Let me write this cable profile once again here. So parabolic cable at the center H is equal to 150 mm. At center it is 150 mm. Okay. Overall length of the beam is how much? 8 meter. Let me write in terms of millimeter. It is 8,000 millimeter overall length. Okay. Now what we want eccentricity at a distance of 3 meter, means at a distance of 3000 mm. We need eccentricity. We need eccentricity E. Okay. Now how to find this eccentricity now? We have the standard equation, correct? Equation of the parabola, correct? Huh? What is the equation of the parabola? We know that equation of parabola is y is equal to 4hx divided by L square into L minus x. This is what the equation of the parabola. Okay, where x is equal to 3000 mm, where eccentricity is needed, means depth of the parabola is needed. Okay, nothing but E only, nothing but E. Here y is nothing but E. Here. Okay, so to calculate here x equal to 3000 mm, L is nothing but length of the beam or length of the parabolic cable 8000 mm. This substitute you will get the eccentricity at 3000 mm. Therefore, y is equal to E is equal to. So with respect to this our problem, y is nothing but eccentricity E. Okay, y is equal to 4hx. 4 into h is nothing but eccentricity at the center or depth of the cable at the center of its span. How much it is? 150 mm. 150 into x is 3000 divided by L square. 8000 square into L minus x. 8000 minus 3000. Okay. By this you will get eccentricity at 3 meter from the left support. Please calculate and cross-check the answer. It is 140.625 millimeter. 140.625 millimeter. Okay. Please calculate and cross-check. Now we got all the required parameters to calculate the bending stress due to prestressing force. That is PE by Z you can calculate. Plus PE by Z and minus PE by Z you can calculate. Therefore, plus or minus. Therefore, bending stress due to prestressing force is equal to plus or minus PE by Z, correct? Plus or minus PE by Z is equal to plus or minus P is prestressing force. How much it is given? 180 kilonewton, 180 into 10 power 3 Newton, 180 into 10 power 3 into eccentricity 140.625 divided by section modulus Z 12.48 into 10 power 6. 12.48 into 10 power 6. Therefore, it is plus or minus, what is the value? If you calculate, it is 2.03 Newton per mm square. Means plus 2.03 at top fiber minus 2.03 at bottom fiber. Okay. Means, sorry, minus at top fiber and plus at bottom fiber. Okay. As per this diagram. Minus at top fiber, plus at bottom fiber. Now we have calculated direct stress due to prestressing force P by A, and we have calculated bending stress due to prestressing force P by Z. What next? We have to calculate stress due to bending stress due to dead load moment, bending stress due to live load moment. Mg by Z and Mq by Z you need to calculate. Okay. Next deadline you write bending stress due to dead load. Bending stress due to dead load, that is mg by z. we need to calculate. First, to calculate the dead load. Dead load of beam is equal to cross sectional area multiplied by cross sectional area multiplied by density. Density is given or not in the problem? So in this problem it is not given. Okay, if it is not given, we need to assume it as 24. Cross sectional area, how much we have calculated in terms of meter square? 91,200 into 10 power minus 6. 91,200 into 10 power minus 6 into the density is 24. Okay, by this we get dead load of the beam WG. Therefore, WG is equal to it is 2.19 kilonewton per meter. Okay, therefore intensity of the dead load or self weight of the beam is 2.19 kilonewton per meter. Length of the beam is given as 8 meter. Let me write the bigger diagram. Below. .19 kilonewton per meter. Okay. The span is 8 meter. 8 meter. Now we want dead load moment mg. Okay. Here, very important students, listen here. Here, moment is to be calculated at the point where the stresses needs to be calculated. Okay, we need resultant stresses at 3 meter from the left support. Let me take the cross section here. Even the eccentricity we have calculated at 3 meter. Similarly, the moment due to dead load and moment due to live load should be calculated at the same point only. Very important. Don't take it as WL square by 8. It goes wrong. Okay, he specifically said that the stresses to be calculated at 3 meter from the left support. So at this particular point, you need to calculate the moment. Then how to calculate the moment at this point? First, you calculate the reactions at the support. Reactions at the support is equal to how much? WL by 2. WL by 2, that is 2.19 into 8 by 2. Okay. So how much you'll get? 8.76 kilonewton. First you calculate the reaction at the support. So I'll write the reaction at both the supports. 8.76 on either side. 8.76 kilonewton. Here also 8.76 kilonewton. Okay. Now this distance is 3 meter. The intensity of load is 2.19 kilonewton per meter. Therefore, moment at XX section XX. Okay. Moment at 3 meter from the left support is given by mg is equal to what is moment of this reaction about this point? It is 8.76 into 3 meter. 8.76 into 3 meter, and it is clockwise moment, positive sign. Okay. It is clockwise moment, positive sign, minus why it is minus? This UDL is causing anti-clockwise moment about the x-axis. Therefore, the sign is minus 2.19 into 3 means moment of this portion of UDL about point x. Okay. So if you convert this UDL into point load, it is 2.19 into 3 into perpendicular distance. Perpendicular distance divided by will be equal to 3 by 2. Length divided by 2. I hope you are understanding. If you calculate the moment, mg is equal to, you will get it as 16.42 kilonewton meter or 16.42 into 10 power 6 Newton millimeter. Okay, this is dead load moment. Okay. Similarly, we have to calculate live load moment. Okay. Finally, you calculate mg by z value plus or minus mg by z is equal to plus or minus mg is 16.42 into 10 power 6 divided by what is the section modulus value? It is 12.48 into 10 power 6. 12.48 into 10 power 6. Answer is plus or minus 1.32 Newton per mm square. Plus or minus 1.32 Newton per mm square. Okay. Now we got bending stresses due to dead load. Similarly, we have to calculate bending stresses due to live load. Bending stress due to live load, that is MQ. Okay, we know the intensity of the live load which is given in the problem. Intensity of live load is how much it is given? 8 kN per meter. It is given as 8 kN per meter. Overall span is 8 meter. And we are interested to find moment at 3 meter from support. Okay. So reaction, calculate the reaction. Reaction at support is equal to WL by 2. W is 8, L is 8 divided by 2. So 32, correct? 32 kilonewton. So reaction at the support is 32 kilonewton. Here also 32 kilonewton. Intensity of the live load is 8 kilonewton per meter. You can calculate the moment at section XX now. Therefore, M cube is equal to 32 into 3 minus 8 into 3 into 3 by 2. Okay. If we calculate, MQ is equal to 60. We will get the answer as 60 kilonewton meter. In terms of Newton millimeter, 60 into 10 power 6 Newton millimeter. Okay. Okay. So now you got live load moment. You can calculate bending stresses due to live load moment. Therefore, bending stresses is plus or minus MQ by Z is given by plus or minus 60 into 10 power 6 divided by Z value is 12.48 into 10 power 6, 12.48 into 10 power 6. The answer you will get as 4.81 plus or minus 4.81 Newton per mm square. Okay. Now in the question it is asked to write the stress distribution diagram. Now you can easily write the stress distribution diagram. You know each and every stresses. You can write the stress distribution diagram. Okay. What is the nature of stress distribution diagram? Let me show you. I explained it in the beginning of the class. Yes. So this is what the nature of the stress distribution diagram. Okay. First you need to write the cross section. Let me write the cross section. Here we have I section. Okay, na? Initially, we have a direct distribution due to pre-stress plus P by A plus P by A. Okay, that value is P by A value is how much? It is 1.97. 1.97. 1.97. Then what we have? Minus PE by Z plus PE by Z. Okay. That PE by Z value is how much? PE by Z value here 2.03 minus and plus 2.03. 2.03. Okay, this is bending stress due to processing force. Then we have bending stress due to dead load plus mg by z minus mg by z. Let me write the diagram. Mg by z value is how much? Plus 1.32 minus 1.32. 1.32. Then finally mq by z, same kind of diagram for live load stresses due to live load. What is the value? Plus 4.81 minus 4.81. 4.81 minus 4.81. Okay, now you can calculate the resultant stress. You can write the diagram for the resultant stress. Before writing the diagram for the resultant stress, you should know the value. Correct? You should know the value. Therefore, F superior means resultant stress at the top fiber is equal to plus 1.97 minus 2.03, then plus 1.32 plus 4.81. How much you'll get? You will get it as plus 6.07 Newton per mm square. Similarly, you can calculate stresses at the bottom fiber. F inferior, it is plus 1.97, then plus 2.03, then minus 1.32 minus 4.81. So if you calculate the answer, you will get minus 2.13 Newton per mm square. So if you know the values, then only you will be able to write the proper diagram. So let me write the reference line. This is the reference line. At top fiber, it is plus 6. Okay. And at bottom fiber, it is minus 2.13. So this is what the nature of resultant stresses. Plus, minus here, plus 6 point F superior is equal to plus 6.07 Newton per mm square. F inferior is equal to 2.13 Newton per mm square. So this is what the stress distribution diagram at a distance of 3 meter the left support. So this completes the problem. If you have got any doubt at any step, please ask. Any doubts here? Okay, thank you. So we'll move on to to this the problems on calculating calculation of the stresses is over. So we have another topic in this model. Let me discuss. That is, please write the headline as pressure line or the thrust line. Write the headline as pressure line or it is also called as thrust line. So this is important for the point of your examination. They will ask a theory question on this pressure line or the thrust line. They will ask you to write about or explain about pressure line or the thrust line. Okay. So before going to explain the meaning of the pressure line or the thrust line, let me take a beam. Okay. Let me take a beam. Understand this clearly, students, because if you do not understand the concept of pressure line or the thrust line, you will not be able to solve the problems, next coming problems. Okay. Let me take a beam. Okay. Having the length L and the length L. Let us take lay load on the beam as UDL of intensity WQ per meter length as the uh, load acting on the beam. As a load acting on the beam. Let me draw the centroidal axis for the beam. This is the centroidal axis for the beam. This is the central axis of the beam. Let me apply a pre-stressing force for the beam. At an eccentricity, E is equal to h by 6. I will tell you why it is applied at an eccentricity of h by 6 only. P, pre-stressing force, P. Okay. Now what I've done, I've considered a beam having a rectangular section, which is acted upon by an UDL of intensity WQ per meter length such that the resultant stresses at the bottom fiber at the center of the span is 0. Okay, assume that lay load stress. Okay, assume that the lay load is applied in such a way that the resultant stresses. Let me write somewhere else. Okay, that lay load is applied in such a way that the resultant stress, if we calculate the resultant stress at center of the span, the resultant stress at the bottom fiber is 0. Okay, in such a manner the load is applied. Okay. Now, if you calculate the stress distribution at different points of the beam, okay, if you calculate stress distribution at different points of the beam, what will be the nature of stresses? Let us see. Okay. Now, initially, if we at this particular condition, no, at this condition, if we calculate stresses at the end of the beam, okay, means stress at the support section. If we calculate, the nature of stress distribution will be, let me write the diagram. So this is what the nature of the stress distribution diagram. This is the centroidal axis. Okay, students. Here the force P. The force P is applied at a distance of how much? It is applied at a distance of at an eccentricity of E is equal to h by 6. Okay, it is applied at an eccentricity of h by 6. The precessing force P is applied at an eccentricity of h by 6. At this condition, the stresses at top fiber will be 0. Okay, let me explain how this stresses at top fiber will be 0. What is the formula we have for top fiber stresses due to precessing force? What is the resultant stress due to precessing force? It is plus P by A. It is plus P by A minus P by Z. Correct? Plus P by A minus P by Z. Let me take that formula here. I am calculating resultant stress due to precessing force. Means there is no moment due to dead load or moment due to live load, because at the end of the beam moment is 0. At support moment is 0. Therefore, this mg and mq will not come into picture at the support section. I hope you are understanding. At the support moment due to dead load or whatever dead load, at the support at the end of the beam, there won't be any moment because it is simply supported beam. Mg and mq will be 0. So we will get only two terms, P by A and P by Z. Okay. Therefore, P by A minus P by Z, P by A minus P by Z is the resultant stress sector at the top fiber. Okay. Now, P by A. P by A is nothing but what? It is area of cross section. It is nothing but area of the cross section. If you assume the beam is having a rectangular section of width B and height h, area will be how much? B into h. P by A is equal to P by BH minus P into eccentricity. How much is the eccentricity? H by 6. P into h by 6 divided by P by Z. What is the formula for Z? Section modulus of a rectangle. It is BD square by 6. Okay. Formula for section modulus of rectangle is BD square by 6. BD square by 6 means B into depth is nothing but H. BH square by 6. If you calculate, what is the answer that you get? P by H. Let me write here. P by BH minus PH by 6 minus PH by 6 divided by BH square by 6. 6 gets cancelled in both numerator and numerator, and this H will also get cancelled. Only the term remaining is P by BH minus P at the numerator and pH at the denominator will be 0. Therefore, the resultant stresses at top fiber is 0. I hope you are all understanding. See, we know that resultant stresses at top fiber at the support section is P by A minus PE by Z. Okay. Keep as it is. Area of section is B into H. P into H minus P into eccentricity is H by 6. I have substituted here. Divided by Z we have. For Z we have the formula of BH square by 6. BH square by 6. So if you simplify this term, finally you will get the answer as 0. Finally you will get the answer as 0. Okay. So, and you will get some value at the bottom fiber. Okay. For bottom fiber, we have the formula P by A plus PE by Z. You will get some value. Okay. You will have some stress. But at top fiber, it is 0. This is what the nature of stress distribution when the precessing force is applied at an eccentricity of h by 6. Okay. Now, for this stress distribution diagram. If you locate a centroid, if you locate the centroid, where you will get? It is a triangle. Okay, triangle. For a triangle, the centroid is located at a distance of h by 3. H by 3 from the bottom. H by 3 from the bottom, which means that the pre-stressing force and the resultant thrust both will coincide at the support. Okay, whatever the P I have written here, it is a thrust. It is reacting thrust, reacting force. Okay, and P written here, it is a pre-stressing force that is acting on the beam. Thrust and the pre-stressing force will both coincide at the support section. That is the meaning. Okay, I hope you understood. Now, same way, what is the stress distribution at the center of the span? In the beginning only I said that the live load is applied on the beam in such a way that resultant stress at the bottom fiber at the center of the support is 0. Let me take a section at the center of the support. Let me extend this. Okay, at the beginning only I have said the live load. So at this point, this mg and mq will come into picture. Correct? mg and mq will come into picture. There is some live load, there is some dead load. Okay, there is some live load moment and there is some dead load moment at the center of the span. Okay, and this live load is applied in such a way that the stress at the bottom fiber is 0. Stress at the top fiber is, there is some value at the top fiber. This is what the stress distribution at center of the span. Okay, so in this case, here we will have the pre-stressing force. In this case, the thrust line. Okay, the resultant of this whole stress at the center of the span will shift to h by 3 from top fiber. Okay, h by 3 from top fiber, or it will shift at a distance of h by 6 from neutral axis or the centroidal axis. Okay, okay, this is centroidal axis. Okay, centroidal axis to top fiber is h by 2. Okay, this is overall is h by 2. H by 2 minus, let me do here, h by 2 minus h by 3. If you do, you will get h by 6. Yes, h by 3. If you do, you will get 3h minus 2h divided by 6. H by 6. So same thing I written here. Okay, in the overall half of the depth, if you deduct h by 3, you will get h by 6. Okay, therefore the thrust line will be shifted at a distance of h by 6 from the neutral axis at the center of the span. Okay, this much you understand. Similarly, if you calculate the resultant stresses or stress distribution at quarter span, means at a distance of L by 4 from any end of the beam, the nature of stress distribution will be there will be some value at the top fiber and there will be some value at the bottom fiber. Okay, per quarter span. Okay, per quarter span, what happens? There will be some value at the top fiber and there will be some value at the bottom fiber. Okay, and for this, if you locate the centroid, no, further the centroid of the thrust means centroid of the stress distribution diagram or the thrust line, okay, will be shifted at a distance of h by 2, half of this h by 12 from the neutral axis. Okay, so here we have pre-stressing force at a distance of h by 6. Okay, this is what the stress distribution diagram at the quarter span. At quarter span. L by 4 at L by 4 distance. Okay. Now let me write the thrust line now. Combined thrust line at each and every point. Now let me show here in this diagram only instead of writing one more diagram. Okay. Now I'll write the thrust line now, students. Okay. Now at support, where is the location of the thrust line? It is at the point where precessing force is applied. You can see here. It is at the point where precessing force is applied. And at the center of the span, where is the location of the thrust line? It is at a distance of h by 6 from central axis. So it is at a distance of h by 6 from the central axis. And at quarter span, where is the location of the thrust line? At quarter span, where is the location of thrust line? At a distance of h by 12, slightly below here. At a distance of h by 12 from the central axis. Okay. Now, if we join all the points now, this is what the resultant thrust line you get for different points. Okay. So the line joining resultant points of the stress distribution diagram is called as thrust line. Okay, what we have done, we have considered a beam with some pre-stressing force located at a distance of h by 6, and by considering a live load of intensity WQ per meter, such that the resultant stresses at the center of the span at the bottom fiber is 0. For that, we have calculated the stress distribution diagram. After preparing the stress distribution diagram, you have located the center of the stress distribution. Okay, at the support we got center of the thrust as h by 6 from the neutral axis. Okay, at the center of the span, the thrust line shifted at a distance of h by 6 from the neutral axis. At the quarter span, the thrust line is shifted at a distance of h by 12 from the neutral axis. Joining all the points together, we will get a line that is called as thrust line or the pressure line. Okay, this is what the concept of pressure line or the thrust line. Okay, in numerical problems, what they will give is, they will give some beam having some dimensions, they will give some loading conditions. He will ask you to prepare the thrust line. Okay, you will be asked to prepare the thrust line at different points. Okay, so whatever the formula, the principle we have used to prepare this thrust line for this particular beam, same principle we will be using for numerical problems. Okay, any doubts in this discussion, students? Please ask. Any doubts here? Same thing you need to explain. Okay, same thing you need to explain. Here I explained. Okay, if you understand, you can easily explain. Understanding is very important. Let me show that. Yes, here I have explained all the things. Okay, I have written a separate diagram for showing the pressure line and the thrust line. Okay, everything is explained. Understanding is very important. If you understand, you can easily give the elaborated explanation. Okay. Any doubts? Any clarifications you need? Okay. Okay, we will solve one numerical problem on this. Okay. Please write down the question, numerical problem. Write this question. All of you go through it. It's a very simple question. Problems on this thrust line are easy only. What is the question here? A prestressed concrete beam of section 120 mm wide and 300 mm deep is used over an effective span of 6 meter to support a UDL of 4 kN per meter. Let me write the diagram. Solution. The cross section of the beam is given, correct? If you want to write the question, please write. In the meanwhile, I will write the diagram. One 20 mm wide and 300 mm deep. 120 wide and 300 mm deep. The span of the beam is given as 6 meter. Okay, span of the beam is given as 6 meter. Uniformly distributed load of 4 kN per meter is given. Okay, now WQ here I have already written here. WQ is equal to 4 kN per meter. Okay, that is the intensity of the load. And he says that the beam is prestressed by a straight cable carrying a force of 180 kN and located at an eccentricity of 150 mm. Let me write the central axis. There is a prestressing force of 180 kN at an eccentricity of 50 mm. Force P is equal to 180 kilonewton. It is acting at an eccentricity of 50 mm. Eccentricity E is given. Correct? Now, what is the question? Determine the location of thrust line in the beam and plot its position at quarter and central span section. Okay, we have to find the location of the thrust line. Okay, let me write all the given data. P is equal to 180 kilonewton. Cross-sectional area of the cross-sectional given, you can get the self weight of the correct. Dead load of the beam you can calculate. Dead load of beam. Dead load of beam is equal to WG is equal to what is the dead load? Cross-sectional area multiplied by density. Cross-sectional area is it is given as 120 by 300 in terms of meters square. It is 0.12 into 0.3. 3 into density 24 standard value. Answer is 0.864. Okay, kilonewton per meter. This is dead load moment. Okay, sorry, dead load intensity of the dead load, and intensity of the live load is also given, that is 4 kN per meter. Okay, therefore W is equal to total load on the beam is equal to WG, load, dead load plus live load, WQ is equal to WG is 0.864 plus live load is given as 4 kilonewton per meter plus 4 is equal to 4.864 kilonewton per meter. Okay, this is the total load. Total load. Okay, I'll tell you why I have calculated this total load. Okay, in the next coming calculation. Okay, now you write the diagram, loading diagram. Total load on the beam is how much? Total intensity of the load, the total intensity of the load that is acting on the beam is 4.864 kilonewton per meter. Okay, calculate the reactions at the support. Reactions is equal to WL by 2. Total span is how much? It is 6 meter. Correct? 6 meter. Okay. The reaction, if you calculate, it will be 4.864 into length 6 divided by 2. Answer is 14.6 kilonewton. Okay. Therefore, here 14.6 kilonewton and 14.6 kilonewton. Okay, reaction I have written. Now here go to the question. So I have done all basic calculations. Okay, basic calculations means I have calculated the dead load, I have calculated the total load, and I have calculated the reactions at the support. Okay, for the total load that is acting on the beam. Okay, now go to the question. It is asked to determine the location of the thrust line in the beam. Okay, we have to locate the thrust line in the beam and plot its position at quarter and central span. You say that you have to plot the position at quarter and central span. Okay. Now what you do is you calculate moment at quarter span and the central span. Okay. To locate thrust line at the quarter span and the central span, first you should know the moment at the respective points. Means moment at quarter span and the central span should be known. Okay. Therefore, even moment at the support should be known. What is the moment at support? It will be 0 only. Therefore, moment at support moment at support is 0. Okay, moment at support is 0. And moment at quarter span means at 1.5 meter, 6 by 4. Huh? You calculate moment at 1.5 meter distance, then moment at 3 meter distance, central span. Okay, therefore moment at quarter span moment at quarter span is equal to reaction is 14.6 into 1.5 distance, 14.6 into 1.5 minus moment of this portion of UDL about this point 4.864 into 1.5. If you do, you will get conversion of UDL into point load into perpendicular distance 1.5 divided by 2. So you will get the moment as 16.43 kilonewton meter or 16.43 into 10 power 6 Newton millimeter. This is what the answer. Similarly, if you calculate moment at the center span or mid span, moment at mid span, either you can use WL square by 8 formula, or like we calculated for quarter span. No, in that way also you can calculate moment at the mid span. WL square by 8 is equal to 4.864 into 6 square by 8 into 6 square by 8. The answer which you get is 21.91 kilonewton meter, or 21.91 into 10 power 6 Newton millimeter. Okay. Now, very important step. See, here the type of cable here given is a straight cable. This is a straight cable. Okay. What is the actual procedure of locating the thrust line? What is the actual procedure of locating the thrust line that we have done? Yes. First, we have to find thrust distribution at the support, center span. Sorry, students, it was an office call. Now, the type of cable which we have here is, it is a straight cable. Okay. For straight cable, okay, if the beam is having the straight cable, we have the direct formula to locate the pressure line. Please note down location of pressure line, location of pressure line is equal to E bar is equal to M by P. This is the direct formula. It is applicable only for straight cables, not for the parabolic or any other profile cables. Applicable for only straight cables. Straight cable. Okay. If it is a parabolic cable, we have to follow this procedure. Okay. Anyway, we'll be solving one particular problem on that type of cable also. E bar is equal to M by P. Therefore, E bar at supports, eccentricity at the support means location of the thrust line at the support will be equal to moment at support 0 by P. Okay. P, we will get 0 only. Similarly, E bar at quarter span is equal to moment at quarter span. It is 16.43 into 10 power 6 divided by pre-stressing force. P, how much it is given? It is given as 180 kilonewton, 180 into 10 power 3. 180 into 10 power 3. So you will get the answer as 91.3 millimeters. Similarly, E bar mid span is equal to moment at mid span. It is 21.91 kilonewton meter, 21.91 into 10 power 6 divided by 180 into 10 power 3. So if you calculate the answer, it is 121.72 millimeter. Okay, now we can write the location of the crust line. Okay, now this is the longitudinal section of the beam. Okay, so this is the centroidal axis. Centroidal axis. So here we have the prestressing force P. Okay, so this is the straight cable P. So at support, what is the eccentricity from the pressure line? From the prestressing line, it is 0. It is 0. Now I am locating the thrust line. Listen here, 0. At quarter span, it is 91.3 mm. Okay, from this point at a distance of 91 point. So whatever the 91.3 mm. So whatever the value we are getting, it is with respect to cable profile, distance from the cable profile. And at the center span, it is 121.72 mm. So whatever the answers we got, it is with respect to the cable profile, not from the centroid, the distances. Okay. Similarly, you will get the similar values on the other side. So finally joining the line. So this is what the thrust line, nature of the thrust line, nature of the pressure line of the thrust line, the pressure line or thrust line. So this completes the problem. Okay. If you have any doubts, you can ask. Otherwise, we will wind up the class. Okay, students, we'll finish the class and we'll continue the next class.